Most experienced engineers arrive at a shared assumption. Implementing the classic Gang of Four design patterns will naturally yield a robust domain model. Traditional software architecture categorizes patterns by their mechanical function. We organize them by how they encapsulate algorithms, instantiate objects, or iterate over arrays. Domain-driven design imposes a different standard. Here, a pattern is only valid if it provides conceptual clarity and accurately reflects business reality. The threshold for entry into a domain model is strict. A pattern must actively strengthen the ubiquitous language, the exact shared vocabulary spoken by both the development team and the business experts. This means structurally pleasing code can actually become a liability. Injecting terms like flyweight or factory directly into the domain model pollutes that shared vocabulary with technical jargon. If a pattern exists solely to solve a software optimization problem, it is merely implementation machinery. It must be ruthlessly excluded from the domain model. We can conceptualize this standard of evaluation as the pattern forge. This is a rigorous filter we apply to standard design patterns before allowing them into the core of a codebase. Patterns that express real business concepts will pass through the forge and enter the domain. Patterns that serve only as technical machinery are diverted into the infrastructure layer. We are going to subject 3 specific patterns to this forge: strategy, composite, and flyweight. We are not evaluating whether these patterns are useful. We are determining exactly where they belong within the system's architecture. Software architecture remains resilient only when we successfully segregate the language of the machine from the language of the business. We start with the strategy pattern. Its textbook definition is to define a family of algorithms, encapsulate each one, and make them interchangeable at runtime. Consider a real-world shipping domain. The industry standard practice is to allow 10% cargo overbooking on a vessel to compensate for last-minute cancellations. In a typical application, this overbooking rule often exists as a hidden guard clause inside a standard make-booking method. This implementation fails the domain-driven test. A non-technical logistics expert cannot read or discuss a mathematical calculation buried inside application logic. The solution is to extract this calculation into a strategy object, renaming it to match the business concept, an overbooking policy. In technical architecture, applying strategy requires multiple, interchangeable algorithms. In domain-driven design, the act of giving a concept a distinct name justifies the object's existence, even if there are no variations to swap. The value of the strategy pattern in the domain is not polymorphic flexibility. The value lies in making a hidden business rule explicitly visible. Next, we test the composite pattern. Its technical function is to treat individual objects and nested compositions of those objects uniformly through a tree structure. To see if this belongs in the domain, we look at the physical reality of the shipping industry. Moving cargo relies on complex physical logistics. Transporting goods from point A to point B relies on a route. Domain experts understand that a massive global route is built by connecting smaller, distinct segments. This diagram models a shipping itinerary, defining a route abstract class and its relationship to a composite route node. It shows how a global route is constructed by nesting specific transport legs and door legs in strict chronological order. Using the composite pattern simply because a developer wants a convenient recursive tree implementation in their code leads to fragile design. The pattern survives the forge here only because the real-world business domain naturally operates as a nested hierarchy. Finally, we evaluate the flyweight pattern. Its core technical motivation is to share fine-grained objects to reduce overall RAM usage and memory cost. Suppose our shipping system needs to simultaneously process millions of identical electrical outlet objects or standard shipping containers. An engineer's immediate instinct is to implement a flyweight factory to deduplicate these instances and optimize system memory. We apply the litmus test. Ask if a non-technical logistics expert cares whether the server allocates 1 instance or 10,000 instances of an immutable object in memory. The answer to that question is definitively no. The flyweight pattern completely fails the test of business relevance. Forcing it through creates negative consequences. The domain APIs become cluttered with factory methods and memory management jargon that holds zero meaning to the domain expert. Exposing flyweight mechanics inside the domain model pollutes the ubiquitous language. It must be strictly confined to the infrastructure layer. We can synthesize these tests into an actionable framework. Before letting a pattern enter the domain, apply this 4-question litmus test. Question 1. Does this pattern represent a concept that the domain experts actively recognize and discuss? Question 2. Does implementing this pattern measurably improve the precision of the ubiquitous language? Question 3. Does this pattern clarify an otherwise hidden business rule, relationship, or responsibility? Question 4. Would this concept matter if we replaced our underlying technology tomorrow? If the patterns in your codebase do not answer these questions, you are building a solution in search of a problem. Forcing a domain to fake the preferred pattern compromises the architecture. If the answer to the litmus test is no, drop the pattern from the domain. Keep your model rigorously focused on business reality, and the code will follow.